Okay, welcome to the Momentum Transfer Model. This is recording number 1, where we're going to go over very quickly the demo that we used to start off our study of momentum, and then take a look at some of the types of collisions that we've got that we can take a look at. So on this page, this is actually the beginning of your unit. I want to say it's somewhere around page, I don't know, 118, 115, around in there. All right, but let's consider what we were looking at on the very first day, where there was the track, right? And then I had the two cars. And there were a couple of different collisions, but we had a blue car and a green car. And depending on what we were doing, we're trying to build a model of what was going on when the two cars hit each other. So the first thing we did a few where, I crashed this one over here into this one. We ultimately, eventually got to a point where we were trying to get this car to hit this car. The one car on the left had a lot more mass on it, and we wanted them to crash and then come to rest, a final velocity of 0. So did that a few times and drew some before and after graphs to take some snapshots of what was going on. And what we figured out is that this one, the blue one, the bigger one, started off looking like this. The green one was going much faster. So we had 4 little squares there. And then afterward, we wanted them both, that's supposed to be on the 0 line, you guys. So we've got nothing there for either one of them, and realize that this does not show any sort of conservation. But someone in the class invariably told me in a very smart way that we could just make that wider. All right, let's see if we can get a second. All right, pretend there were 4 blocks there. That's what we're going for. All right, we went wider to compensate for the mass, to counteract all of that velocity there, and we could still conserve. So this idea of mass and velocity together, that's the term we call momentum. And so that was kind of the new deal, the new big deal. So our new fundamental principle here is that momentum, which is our mass multiplied by our velocity, is conserved. And the term conserved in physics or science in general means it's not created or destroyed. Like once you have some, you can transfer it, you can move things around, but it doesn't really go away. All right, it's not created or destroyed. So we had 4 blocks of momentum here. We've got 4 blocks of momentum here in the opposite direction because it's a vector, and they canceled each other out, so we ended up with 0 at the end. All right, now here, if you look at this, considering this one is in the 4th quadrant versus the 1st quadrant, they are going to naturally cancel each other out to begin with. So you could say, you have 0 momentum to start and you have 0 momentum overall to finish. Notice we're talking about total, not individual objects, because obviously the blue car is moving and the green car is moving as well. So this was kind of the big picture item for day number 1. We haven't done a whole lot of descriptions of what things mean and symbols and things like that, but I will probably come back to that a little bit later on in this video. Day number 2, we went into the computer lab and we're looking at this demonstration. I didn't grab the whole thing, but like for example, we've got this first one here where the blue cart is initially at rest. So let's say that our blue cart has a mass of 2 kilograms and I don't know, whatever, maybe you made this one 1 kilogram. They started off with no velocity for the blue cart. Let's assume maybe you have a velocity of 4 for this cart. So 4 meters per second here, 0 meters per second here. All right, what you would notice, and then of course you crash them, which I did not do, right? But there we go. All right, so if we are, let's see, they both ended up moving when they were done slightly. So these numbers, they're going to stay the same, certainly. And so we're looking at a total of 4, I don't know, let's say 1 and 2, right? You get these new velocities that then you would pick up from over here. And you would have, let's see, what did I just write down? 2 meters per second for this one, and 1 meter per second for this one. After which, See, so we've got a momentum of 2 and another momentum of 2 over here. When you look at your system totals, you notice that you've got 4 plus 0. So you've got a total momentum of 4. And here you also have a total momentum of 4. Right? If you look at the change in momentum, this is going to be your final minus your initial momentum. I wanted you to take this value first, that's your final, minus your initial momentum of 4. So the overall change for the red card is minus 2 kilograms meters per second. Over here, you would do final minus initial, and you would get an overall of plus 2 kilograms meters per second. So what we would notice here is that we end up with exactly the same momentum that we begin with and we finish with. And whatever goes down gets picked up by the opposite object or the second object in the collision. So again, this is showing us conservation. And that particular activity, you went through several different types. You notice this one, it's called an elastic collision. It's not defined, but if you were watching this collision, you would notice that these two objects, they bounce off of each other, right? They both end up moving at the end. I mean, maybe they move in opposite directions, maybe they move in the same direction, but they bounce off of each other. And that is a real rough and dirty way of explaining elastic collision. There are other types of collisions that we also looked at in this activity. The second one was inelastic. And then the last one, which everyone was excited to try, was the explosion. All right, we're going to go over what those mean in a little bit. But again, quick and dirty way to explain it. Inelastic means they stick together. Explosion means they start off stuck together, but then they blow apart from one another. So we'll definitely spend some time looking at those in just a minute. Now, let's, in fact, let's go back to here a little bit. I can actually fill in some of those. I mean, doesn't fit my little graph here perfectly, but considering it's my workbook and I can do whatever we want, let's take a look at the ideas we've got here. An elastic collision. All right, that is when the objects bounce off of each other. All right, we could say an inelastic collision. Our objects stick together. And an explosion is when your objects are together. Let's put in a little E there. They usually start off at rest, then they blow apart. In opposite directions. Now, this idea, let's go back a little bit. All right, momentum, or m times v, that gets a symbol of lowercase p. Not sure why they do that, but they do. And also momentum's units. Let's think about this. Mass is measured in kilograms. Velocity is measured in meters per second. So that is the unit for momentum, whether we're talking an elastic collision, an inelastic collision, or an explosion. All right, those are the units of momentum. All right, so we're going to flip to this one now. How can we use this information? Well, one of the key things that often happens when we do these sorts of, when we look at momentum, is we end up calculating unknowns. You look at a collision, and you're asked to find, say, a final velocity for an object. Maybe you want to find a combined velocity for an object, but we can use the idea of conservation of momentum in order to do that. And I'm going to show you a couple of examples of that. I'll show you an elastic, an inelastic, and an explosion, so you can get an idea of how they work and what that math looks like. You'll have to bear with me because I didn't pre-calculate these, so I'm going to have to run my calculator at the same time as you are. Okay, so if I read this question, notice So it mentions here the final velocity of the second ball if the first one's final velocity is negative 1.5 meters per second. This tells me right away that the balls bounced off of each other. All right, so the first ball is going to go back this way, and it's going to have a final velocity of negative 1.50 meters per second. And this one, I don't know, but it's going to bounce, which tells me that this is inelastic collision. So that's one of the first key things that I need to know. Now, the rest I can figure out using conservation. So let's go through how you would solve a problem like this. All right, so initial momentum has to equal the final momentum. And then the question to ask is, well, what has initial momentum? All right, there's initial momentum for ball number 1, and there's an initial momentum for ball number 2. And in the end, you also have ball number 1 and ball number 2, but don't be fooled, they're not the same. Okay, these are initials, and the other ones are finals. Okay, momentum is mass times velocity. So the mass of ball 1 times the initial velocity of ball 1 plus the mass of ball 2 times the initial velocity of ball 2 equals mass of ball 1, final velocity of ball 1 plus mass of ball 2, final velocity of ball 2. Now I can start filling in the values that I have. Be careful for the negatives. They mean something. All right, if you're going to the left or down, we use negative as a velocity, and you need to account for it and then let the algebra sort itself out. So don't leave them out. So I'm going to drop the units because I'm trying to save myself a little space. All right, but I'm pulling out the numbers from the questions, or from, I should say, really from my diagram. And so 1.85, 1.3. All right, oh, actually, that's got to be a negative 1.3, isn't it? Because it's moving to the left. Almost missed that one. Now let's do the final. All right, so M1 is still 1.5. And we know that the final velocity is negative 1.5 for that one. And then my second one is 1.85, and I want to figure out VF. Now don't be fooled, things aren't going to cancel. All right, things just don't easily cancel for this one, but I can actually see what I can squeeze in here. All right, so I'm going to get 3.45 for that, minus 2.405 equals, and this is going to be negative 2.25 plus 1.85 VF. After that, it's pretty straightforward algebra, right? So I'm going to subtract 3.45 and 2.405. Ah, that was not what I meant to do. Hang on a moment. All right, so over here, we've got 1.045. Sorry, I'm running out of space over here. All right, equals negative 2.25 plus 1.85 VF. All right, now I got to move this over, so I'm going to add this to the other side. I'm going to move this whole thing up into the upper right corner, so that way it is easier to see. 5. All right, so 3.2. And then we just divide both sides by 1.85. And we've got it. Not really tough math. Trust me, you guys have been doing much, much tougher stuff. But it gives you an idea of what's going on. So it makes sense. This ball is going to the left after the collision. This one is going to turn around and go this way after the collision. So you can do some predictions there, which is kind of nice, kind of helpful. But that one's elastic because they bounce off each other. Our second example, if you read this one, 15,000 blah, 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 railroad card, right there. It tells you that it is sticking together. And that tells me that this is an inelastic collision. So I have two things that hit each other, and they're going to stick together when they're done. That means they're going to move, their final velocity is the same for both objects. That's important to know. Okay, so again, we start in the same place, initial equals final, and you ask yourself, okay, what's moving? So I have car number 1, mass of car number 1, velocity initial. I have a mass of car number 2 with its initial velocity, and together they're stuck after the collision. So you would add the masses up, and they're going to move with the same final velocity, right? Because they're stuck together. Now, it tells you that the first car is at rest. So this is going to drop out, right? Because 0 times anything will be 0. Mass of the first car is 15,000. Initial velocity, 2.45 meters per second. Then I've got 15,000 and then 12, gosh, I covered it up. I can't even read it. All right, but I think it's 27,500 when you add those two together times VF. Really, really straightforward math from there. So 15,000 times 2.45. Some quick division. Now again, watch out for negatives if things are moving in an opposite direction. The algebra will follow. And so if you end up with something that does have a negative answer, just write the negative. It tells me direction. All right? But that one is pretty easy. The main trick about inelastic is right here. The fact that they stick together and then they travel with the same final velocity. Okay, our last example for this recording about conservation is going to be this one, which is an explosion. All right, so blah, blah, blah stands on a low friction cart. She is at rest. She then throws a heavy rock, giving it a speed of 7.5 meters per second. Now, I can tell right away, because I've been doing this a while, that this is an explosion, but you may not recognize it. So let me draw you a picture. So here's the girl. She's standing on a cart. Let's assume it has some wheels, right? And she is at rest. She throws a heavy rock. So we figure she's got the rock in her hand, right? This is the initial set of conditions. Then what's going to happen is she's going to throw the rock, right? The rock is going to go that way. She and the cart are going to go that way, right? You see this when you talk about shooting a shotgun, right? Recoil on a gun, or you know, maybe you've seen those physics demonstrations where someone is like sitting on a cart like this and they have a fire extinguisher and they like shoot the fire extinguisher. It's the same thing. All the gas goes this way and then the other person goes this way. So that's an explosion. You have something that is all together to begin with. And notice this one's at rest. It could be moving to the right or to the left as long as all the pieces are together, and then they are no longer together. Something gets thrown or pushed or shot or something like that, and it goes the other way. That's called an explosion. All right, so how do you solve a question like this? The main difference here is that the combination of mass is at the beginning versus the end, but the basic principle is the same. You also hopefully can see that since I'm going in different directions, this is going to have a negative velocity and this one's going to have a positive velocity. Of course, that's going to depend on what you denote as positive or negative. I'm usually not too fussy as long as you end up with both. All right, now, when you're dealing with this, if there is no initial velocity to start with, your initial momentum is 0. I don't want you to go too fast through the algebra and not set it up properly. All right, but final velocity, you're going to have this for the girl, right? And you're going to have mass times final velocity for the rock. Okay? Actually, let's be fair. It's the girl and the cart. They're both together. So considering you've got that, this is how you're going to set it up. Now, a lot of people right away, they just set these two and they skip the 0 part and they just put this over here right away. Don't do that. Don't do that because you're going to mess up your negatives and stuff. All right, I don't even know if I can erase this properly without getting rid of everything important. We'll try. There we go. All right, set it up this way. That way you have all the moving pieces that go with it. Okay, so the girl is on these two carts. So the mass of those two items together is going to be 25 kilograms, right? We got the 2 cart and the 23 kilogram girl. And the rock gets the speed, right? If you look at this, that's all about the rock. We want to know what her final velocity is, right? The rock has a mass of 8.9 kilograms and its speed is, shoot, I underlined it and I can't see it. I'm going to guess that's what it is. Maybe I'm reading it wrong, but hopefully not. Okay, now do the math. You can tell this is going to get multiplied and then it's going to get moved over here. So it's going to end up being negative, all right, which is going to just tell me in physics language that we are going the other way, right? That it is going the other way from the girl in the cart. That's all right. That's what we would want. All right, so my velocity is going to be negative 0.267 meters per second, and I want to leave it as a negative. All right, that's important. So, momentum, conservation of momentum. Just a few reminders. Momentum isn't created or destroyed. It is simply transferred, just like it was transferred here. Remember? This one lost momentum, this one gained momentum. So we can transfer momentum and we can use that idea to figure out all sorts of different types of collisions, ones that bounce, ones that stick together, ones that blow apart from each other. All right, so a lot of stuff in there. Some of it I know we have not covered yet, but we will be. So now we're ready and up to speed. So on to the next one.